Hi, this is Zilal.
This is Sahil.
And this is Mustafa.
This is Data Cleaning Project of Theory and Practice of Data Cleaning course. The problem is raw data is messy, full of inconsistencies, duplicates, missing values, and errors. Data cleaning is the most important and underappreciated step for any machine learning system, and garbage in, garbage out. So it's very important to clean the data because inaccurate data means wrong decisions. Dirty data wastes storage, time, and money. Business insights become unreliable. Our goal to transform from chaos to clarity, to transform data into trusted information that fuels growth, impact, and value. Our project used New York Public Library to conduct an end-to-end data cleaning using the various tools and techniques that we have learned throughout the course. For example, we used OpenRefine, SQLite, and Python. On top of that, we used SnakeMake to automate the pipeline. Data quality as fit for purpose. There are general data cleaning steps that can be applied to any dataset. For example, removing leading, trailing, white space. However, the data quality should be also fit for purpose, where the clean datasets are free of defects and possesses the features needed for faster decision making, reduced costs, and increased revenue. In our project, our use case was what was the average dinner price per American menu in each decade from 1900 to 2000. So filtering step here is very important to reduce storage and optimize the time needed to ingest the data.
And here we outline the iterative nature of data cleaning by showing the cleaning life cycle. It's rarely a one-pass process. So if you fix one problem like missing prices, it may reveal another one, such as inconsistent date formats. So cleaning is a loop. You want to profile, clean, reprofile, and repeat. The cleaning life cycle ensures that we address errors systematically and revisit earlier steps when needed. So our approach with the NYPL dataset aligns with this pattern, and we use tools like Python, Pandas, and OpenRefine to iteratively filter, cluster, and correct inconsistencies. This transformation of data resulted in a more high quality and reliable dataset that we were able to use for further analysis. And the next slide contains an overview of the steps that we took specifically for this project. So here we can see the entire pipeline that we built for the NYPL project. First, we ingested the original CSVs from the archive. This is completely raw data, so it's full of inconsistencies, missing data, and some other quirks. We performed an initial filtering and cleaning to take only the columns relevant for our use case, such as date, currency, price, and IDs. And as Zulal mentioned, we also filtered date based on the decades 1900 to 2000. We also removed outliers such as dates outside of the normal range and unexpectedly high prices that were unreasonable, like prices above $100 even. From here, we can derive a new column giving the decade in which each menu is taken from, and we join together the menu item, and dish tables together to create a unified data set. And this unified data set combines decade and price information. OpenRefine was used to further cluster similar strings, specifically in the case of the event column, which had things like dinner, supper. It had other items like breakfast, lunch, but we want to filter only dinner items. So we clustered all of these together. And we were also able to ensure that the currency values were all American dollars for consistency and using American menus only. Finally, at the end, we were able to calculate the aggregate average price per decade from this final clean data set, which was then used for visualizations and trend analyses, as shown in the next slide. So here we can see the final results for the average dinner price per decade. So we can note here there's a general upwards trend from the earlier to later decades, which is expected due to inflation. You see in the 1900s, we have menu items under $1, and then when you hit the 1980s and 1990s, it goes well above $5 to $10. We do note an interesting anomaly here across 1980 and 1990, where we see a big jump and then we drop off. Investigating this further, we mostly attribute it to having a small sample size of restaurants in these decades. Even if we have a lot of dishes, if they all come from the same few restaurants, and say all these restaurants are more higher end than average, the result will end up being skewed towards the higher end. Additionally, we found that in 1990, we had some unexpectedly low prices that brought down the average. And this was thought to be due to the inclusion of beverage prices, which were lower than actual meals. So there were some prices that were in the $1.50, $2 range, which might have been soft drinks. In the future, it might be interesting to see how this changes if we filter based on dish type as well, to only try to include meal items. In the next slide, we will go over some lessons learned.
To make our workflow more reproducible and easier to revisit, we automated everything using SnigMake, as seen in the diagram, our workflow. This helped us keep track of each data cleaning and preparation step. So if we or someone else came back to this project in 6 months, this workflow graph shows the full pipeline at a glance. This kind of provenance is especially valuable in long-term or collaborative projects to remember the exact steps. Next slide. Throughout this project, we learned a few key things about working with real-world data. First is that sample size matters a lot. If there's not enough data to begin with, no amount of cleaning will magically fix that. We ran into this especially with later decades that had very few dinner menus. Secondly, reducing dataset size early made our workflow smoother by filtering down millions of rows to just what we needed. We avoided unnecessary complexity and could clean much more effectively. And finally, using a mix of tools, OpenRefine, Python, Pandas, SQL, gave us both flexibility and precision in handling different challenges during cleaning analysis. Next slide. To wrap things up, we want to emphasize one core idea, garbage in, garbage out. If your data is messy or poor quality, the analysis and results will suffer, no matter how advanced your tools are. People say that data is the new oil, but just like crude oil, raw data isn't valuable unless it is refined. So good data cleaning isn't just helpful, it's foundational.
Thank you.
Thank you.
Thank you.